Good morning, everyone. My name is Chen Jiayun from Institute of Information Engineering, Chinese Academy of Science. Very honored to be here to present our work named RContainer, a secure container architecture through extending ARM-CCA hardware primitives. And the container have become widely adopted in cloud computing platform due to their efficient deployment and higher resource utilization. However, their weak isolation has always posed a significant security concern. Even worse, the problem is more than to only protecting a container against a compromised OS, host OS. It has becoming it becomes that how to achieve the goal that the strong isolation and minimize the TCB and minimize the overhead we look at the container security from this security insight. The first one is isolation between container in both user space and the kernel space, and also minimizing the highest privilege code and also the scalable security features. So we first talk about the ARM new architecture named confidential compute architecture, also as known as CCA. It is introduced in ARM v9-A several years ago. It has 4 physical address space. For the normal path for the normal world, the secure path for secure world, and the realm path for realm world, which is newly added in CCA. And the Granule Protection Check mechanism is also a significant mechanism of ARM-CCA architecture. The key part of ARM-CCA is the Granule Protection Table, or GPT. It protects memory by defining access permission for physical address space. The GPT managed by firmware in EL3, and it is checked happen after the MMU checks. If the GPT says no access, the access is blocked. Even though the memory MMU allows it. This makes the CCA isolation flexible and powerful. But there's a problem. Containers aren't really suitable for running in the realm world. If we put multiple containers in only one realm machine, realm OS, they have to share the same kernel, which weakens isolation. On the other hand, if we give them each container its own realm OS, it is too heavy and adds a lot of TCB into our system. Neither options is ideal. And the second challenge is protecting the TCB when only a small part of it runs with the highest privilege. The question is where we should put our TCB into our system. The first solution is to deploy the TCB in the secure or realm world. If we put the TCB in here, we will get a frequent word switch overhead, and also introduce a large TCB included in the secure or realm world. Another solution is to deploy the TCB in normal world by page table control. Like the previous work named nested kernel. We separate the page tables for those components. For example, one page table for the traditional OS and another page table for our TCB, and we set all the page table as read-only page table, and then the isolation. But it will cause frequently TLB flashing overhead. So both options are not ideal. Here is our thread model. We assume that the system starts out safe, but might get compromised later. And the container OS hypervisor and other components may be compromised. And also physical side channel DOS attack are not out of our scopes. So here came up with our RContainer. It is a new secure container architecture that protects the container on the untrusted OS and enforces strong isolation within a minimal TCP. It uses a mini OS in EL1 to deprivileged OS and shim-style isolation to limit the impact of the containers on the kernel. The first one is mini OS. It is a compact and basic OS running in the EL1 alongside the deprivileged OS. It has mixed page table for tamper-proof protecting and the memory management and also control flow protection. And now I will introduce the mixed page table. The mini OS is very so we use the same MMU page table for all the components on our RContainer system, but we give them different GPTs. For example, different GPT, also the different L0 page table branch. For example, we give them, for example, the privileged GPT is used by mini OS, and the OS GPT is used by the traditional OS, also the deprivileged OS. As you can see in the picture, as you can see in this picture, it is OS GPT, and the mini OS related memory access is to be set as no access. So in this way, the mini OS memory cannot be accessed by the deprivileged OS, keeping things secure. And then the security compatibles of mini OS. First is the mini OS does a few key things. For example, the memory management. It maintains GPT at the software level and has a lightweight memory allocator. And also it has control flow protector. It has exception interposing and responsible for switching between OS and different containers. Then the shim-style isolation. Isolation between containers in both user space and also the kernel space. It is based on our observation that the first, while most attacks originate in the control plane and then impact the data plane. Also, the data plane requires stronger isolation for containers. So the containers are instantiated within the kernel's data plane through the multiple con-shims. Okay. So we give each con-shim a separate shim GPT. Each con-shim has its own GPT. So it's limited to access only its own memory. So the other containers memory, the mini OS memory, and the deprivileged OS memory cannot be accessed by this con-shim. And the container lifecycle protection, we first introduce the both integrity. The deprivileged OS is loaded and measured by EL3 secure monitor. Then both is normally and the mini OS allocates memory for the con-shim and records the system call stack, shared memory, and the private data. And then the tasks, when we creating tasks, mini OS validates and logs the address of the new task structure and the page table. When terminate tasks, mini OS will delete this structure and clear all the memory of these tasks. Then the memory as the most important things. Then the memory page fault handling. We have fast and slow page fault workflow to keep things running smoothly. The first one is faster page fault workflow. Mini OS maintain a secure memory pool in Mini OS, and during the fast workflow, it uses a lightweight page-table handler to allocate memory from the memory pool. And when the memory pool is exhausted, then the workflow we use is in deprivileged OS. It is by traditional memory management handler. And then the I/O protection. Actually, disk I/O and network I/O are not in our scope because we want to have an application layer to protect their I/O data. But our RContainer can protect DMA, protect our container against DMA attack. It is because SMMU GPT can also limit the access of SMMU memory. So here is the implementation. We made two prototypes for RContainer. The first one is FVP prototype for security evaluation. It is based on ARM FVP. And the second one is hardware prototype for the performance evaluation. We implement based on hardware developed board named RK3399. It is our ARM V8 developed board. Here comes the security evaluation. We tested about 30 CVEs and found that most attacks happens only at runtime. And our analysis shows that only about 2.7% of the ATF codes is for runtime, and the other codes, such like boot process, may be they may be covered after loading. And our TCB is very small. It has only 2,600 line of codes, and including more than 100 in EL-DELO, more than 2,000 in EL1, and 130 line of codes in EL3. TCB in EL3, as we know, EL3 is the highest privilege, so we compared the TCB in EL3 with Shelter and other previous work. Shelter has 2,000 line of codes. Even it is continuously growing when the new security features added. Next, the application workload. We made a performance evaluation using some application workloads, and the result shows that it has less than 10% overhead on the real-world application, and it is much better than virtualization method. And also, we compare with Shelter. The average overhead in RContainer is reduced by 5.7 compared to Shelter. And then the life cycle cost evaluation and concurrent overhead. The conclusion is, so in this work, we introduce our RContainer, a new secure container architecture via extending ARM CCA mechanism, and it protects containers on untrusted OS and enforce strong isolation among container among both in user space or kernel space, and it has lower performance overhead without container modification, and it has minimal TCB in the highest privilege, as we know as EL3. Thank you. If you had some more questions, be free to ask.
Samuel Giroux, MIT Lincoln Laboratory. I guess maybe I'm a little confused on the threat model here. So even outside of a confidential computing style environment, the big problem with containers is that they're basically an operating system construct, right? So you've got the operating system is artificially partitioning its internals, and then mixing down different parts and say the networking stack and so forth. And I don't see how you've addressed any of those kind of issues here. Can you maybe expound on that a little bit?
Did you, did you mean the?
Well, so you talked a lot about shimming and basically separating the containers and different parts of the system from each other, but not about how like you've partitioned the OS or how you're protecting container A from container B. Does that make sense?
Yeah, we protect container by isolate the container's memory.
But the containers fundamentally roll through the operating system, right?
Yeah.
So the operating system gets the data from container A. How does it not just share that with container B immediately? Like,
okay,
maybe we should just take this offline.
We use the con-shim to put some important procedure out of the deprivileged OS and make some make some as an instant. Every con-shim is an instant of some function of the host OS.
Okay.
And we also we put the con-shim and the container as a combination and protect their memory as a total.
Interesting. Okay. I'll take other questions offline. Thank you.
Thank you for your questions.
So you also mentioned about some CVEs. So are those your motivation, or your system can defeat those kind of attacks, bugs? I was also confused there.
It's about the 30 CVEs. From the CVEs, we get the. From this CVE, we found that most attacks occur at runtime. It is to show that it is to prove that the runtime code, in the ATF is actually very small. It's about only 11,000 line of code. It is very small. So we compare this 11,000 line of code with our TCB. Yeah.
I see. Any other questions? We can take one more question. Okay. I guess that ends the session. I want to thank all the speakers again, and also thank Jiawing again. And
thank you.